All right, so for this, I'm going to be showing how I created a basic wind tunnel for a project. I'm going to be going over the geometry creation all the way to the results. All right, so just to show the geometry, this was let me move this, there we go. This was the initial geometry I was creating. I wanted a test section velocity through here of 15 meters per second. So I need to figure out what the velocity inlet should be. Um, and then as I go on later, I'll get all these things. So I have my workbench pulled up to start. I'm assuming most people watching this know how to create a geometry, but just in case you don't, that's fine. So you would right click this, right? Okay. You would right click that and you'd press new design model or geometry. Mine says edit because I've already made one, but you would press new. All right. So I guess I can do edit. Why not? Edit geometry and design modeler. Give that a moment to load. All right, so when you initially start this, you're actually going to sort of see this at a diagonal, right? And you're not going to see anything whatsoever. So first things first, you want to set it to the XY coordinate. So you basically want to press Z. You need Y to be facing up vertically and X to the right. All right, so as you can see, XY plane, right? And then what you would want to do is you want to check your units. I'm in meters, which is set to, which is fine. And then I would begin drawing, right? So you have all these different tools you can use. I use the rectangle and the line tool for this, right? So I began with the rectangle from the origin, which would be my test section. And then when you make that, say you want to set your dimension exactly, what you would do is you would click and drag from an edge, right? It could be even a circular edge, and it would give you the diameter. It's going to give you an exact value. So for instance, I don't know why I dragged it so far, but H2 is 1.2192. And as you can see, that's the correct length for my test section, right? All right. Or for instance, this should be 0.889 in the back. And if we look, 0.889. So basically what I did was using these rectangles and lines, I created this basic geometry, right? It's not going to come filled in yet. And you basically want to have a closed geometry, right? You don't want this geometry to be open. But once you have your closed geometry and there's not extra lines inside, make sure there's none. There should be no lines, nothing going on in here. You're going to want to go to Concept, Surfaces from Sketches, click any edge, doesn't matter. Click Apply. It should turn like a bright blue, and then click Generate at the top here. And you should have this gray filled in area, right? Wherever you see filled in area is going to be where there's airflow. So there's going to be no airflow out here. The airflow is fully going to be through here. We're going to treat this as our inlet. We're going to treat this as our outlet. So where you see gray, there's airflow. So this is good. We're going to minimize that, bring up my workbench, and next we would go to mesh. So I'll just double click. The mesh is usually going to take a bit longer to load. It'll take, I don't know, 10, 20, 30 seconds sometimes, right? So you just got to be patient. If it doesn't instantly start, you don't need to keep clicking it. It's just doing its thing. So once you set it to the XY again, this is basically what you're going to see to begin, right? So this is good. Now, if I were to click mesh, you can see this is what we got going on, but it's not going to look like this, and that's okay because there's something which is mesh sizing, right? So element size is 0.001, right? Say, as you can see, as I zoom in, you have all these little squares, all right? But now let's say that let's just say I'm not satisfied with that. I'll do like, let's say 0.005 I'll do, and then depending on how long it takes, whoopsie. 0.005. Depending on how long that takes, I'll come back. Now you can do all these different things, right? You could like right click, you can do sizing, right? For the edges or for inflation, but I'm not gonna do that in this instance. This is simple enough. So I'll click generate and then I'll come back when it's ready to go. Progress. All right, so it took too long, so I just ended up doing an edge sizing. I almost has a 0.005, so that's good. Right, and then for name selections, to name your selections, you're just going to want to click whatever edge or face and then press N, right? So I would name that inlet, for instance. I already have it. So, and then if you click on it, it shows you what it pertains to. So inlet, outlet, and then symmetry. You can name this like top wall, bottom wall. You can name them together, which is what I did. You would just press Control N and select them at the same time. So that's fine. All right, so now what we're going to want to do is we're going to minimize that. We're going to right click and update our mesh. All right, now we're going to want to pull up our setup, so double click. Yes. Double precision, I'll do 4. This depends a lot on your computer, so if you perhaps have a really slow computer with not a lot of cores, you may want to stick with 1. If you have a lot of cores, you may want to do more. The more cores you can do, the faster, but it'll have issues if you put too many. Mine crashes if I do. So we're going to do start. Excuse me. Give this a moment to load. All right, there we go. So now you can go to models. You can change this to whatever you want. I'm going to do viscous, and then I'm going to do should be K omega SST, I believe, right? Is what it should come up to. Yep. It's going to be good for wind tunnel flow, so that's what I'll use. Materials, you can edit it here if you want to. You just right click, but I'm going to leave it as is. Boundary conditions, right click that, or double click that, sorry. Inlet should be velocity inlet, and I've already just through uh, making some calculations and testing earlier, I know if I want 15 meters per second, in that test section, I want roughly 5.85 meters per second for the free stream velocity. So that's fine. Outlet should be a pressure outlet with 0 gauge pressure. I'm not going to select prevent reverse flow for this. Symmetry, I'm actually going to change to wall. I'm going to make that a no slip wall because we're using symmetry will basically allow slip, right? So there'd be no point in using viscous turbulent flow just to then, right, ignore no slip condition. So I'm going to leave the wall like so, right? We go to reference values. We want to compute from the inlet, which is good, right? And then for initialization, more settings. It'll start as 10, but I'm going to do to 25. And then for calculations, I'm going to do it to 1,000. You could press calculate. If you had already initialized it, you could press calculate then, or you could just right click once you have your initialization set to what you like, initialize and calculate. Now it's going to do its thing. So we're done already. With the initialization, at least, still need to do the actual um, iterations now. All right, so we met our residual pretty quick, so that's nice. Um, so now if I look at what I need to pull up for this project, first thing I need to do is pressure velocity, total pressure, and dynamic pressure contours, right? So what you're going to want to do is go to results, contours, new, and then you can make your selections here. I already have some contours pulled up, so I'll start with the static pressure, which is what I would basically have as the default for pressure. Named it accordingly, select all your surfaces, compute, save and display. Right, this is, I'll explain in a moment more why this is, well, I can just explain now. This is to be expected, right? As the contraction zone moves or squeezes the airflow into a tighter space, assuming that mass flow rate has to stay the same, then velocity has to increase, and then because of that we see an increase, well, we see an increase in velocity, but as you can see, a decrease in pressure, and then as our diffuser expands it, right, like the pressure is going to rise again. All right, so now we do the same thing for velocity, but we'd set contours from pressure to velocity, velocity magnitude, compute, save and display. All right, so now even though we have slightly higher velocity through here, right? In this middle portion of this test, right? You're never going to get perfect flow off of that because it's an edge, especially. So in this middle portion, this will get us 15, and I'll show the graph in a moment. If we zoom in, we can see our boundary layer, which is good, where that no slip condition is occurring. So that's as we would expect it. And then I believe the next one they wanted was dynamic pressure, which is actually very similar, or the equation for it is similar to kinetic energy, interestingly. And if you see, this is almost looks like sort of like an inverse to the static pressure, which is interesting. All right, so here's our dynamic pressure, right? And then we can see if we go to our total pressure, which is actually just our static and our dynamic together. And you can select all these, just set the pressure and then select that drop down. Save and display. Right, so here's our total pressure. Right, we have our high pressure on the edges for here, right? We have a lower pressure in the back here, which is more due to our absolute pressure, right? And so this is good, right? Next, we want to show the streamline patterns in the wind tunnel. So to do that, I'm actually going to go to the workbench and I'm going to bring up the results. Double click that, give that a moment to load. All right, here we are. This is good. As you can see, there's already some stuff going on, but once you set this to the XY for your first time, all you're going to see is this black outline. So now, just to show you actually, I can actually show you what it'll look like. So let's go to our lines. Assuming this will load, please. There we go. This is what it's going to look like for you, right? Now what you're going to want to do is you're going to come to Streamline. You're going to press that. I already have it, so I'm going to edit this. And now you're going to want to, this is going to be blank. You're going to want to set this to inlet to the start point. Our variables where we want velocity. And I want to say it starts with like 25 points, but I'll just demonstrate what's going on. So say let's do 25 points, right? Apply. I pressed apply. Oh, sorry, I forgot to select it so you can see it. So as you can see, there's like 25 equally spaced points, right? And it almost looks like our velocity contour. This is sort of almost showing the behavior of, where these streamlines are going direction-wise. But say I wanted to do more, so this is just going to control the number of points. So let's do 50, for instance, right? Right, there's obviously more streamlines now, right? Say I wanted to do, say 75, right? I think everybody sort of gets the point, and realistically, if we did enough, let's do like 150, for instance. It kind of just starts to look like your velocity contour if you put too many, right? So I'm going to dial it back a bit. I'll do like 70. So I'll probably use something around here for my project, but this is what it's just a good demonstration to show. And then let me pause real quick. Hold on. Recording progress. Sorry, there's some background noise, so I was just closing my door real quick. But so there, those are your velocity contours. So next up, along the center line of the wind tunnel, right? Center line. We want to plot the variation in pressure, velocity, total pressure, and dynamic pressure. Now can be a little tricky because I don't think you can directly use total pressure and dynamic pressure, so I had to insert the equation myself, but I'll show how to do that in a bit. So let's start with making that center line, and then let's start with our pressure. So let's hide these for now, just to simplify things. So what you're going to want to do is location, line, right? Name this whatever you'd like. I'm just going to X this out, right? But I named mine horizontal line to begin with. And I'll just double click this so I can edit it. So I'll show you. So this is what you're going to see, right? So now this first point relative to the origin is where this line is going to begin from horizontal to horizontal, right? So say I put this to 0, since I made my origin from this rectangle, the line would start here, right? If I put this to like 2, the line would maybe start like around here, right? So now, since I started from the origin, this would be negative 1.1176, as you can see, right? And then 2.74 is this section and the diffuser added together. Now, this portion is going to be the points for the y-axis of this line. So say I'll just change it because why not? Say I changed it to, let's say, 1, right? The first point's now going to start at y equals 1, right? Once again, from the origin. So change it back to 0.3048. I think that should clarify. Okay, so that's that. And then for samples, when I plot it on the graph, if I do should start with, I want to say 25 samples when you first start. I go up to 100 because if you take too few samples, the graph is going to appear choppy. The curve isn't going to be smooth. So I go up to 100, right? So now that we have that done, right? Apply, nothing's going to change, right? I want to plot the pressure. So what I do is I come here, go to chart, insert whatever you want the name to be, right? So you're going to see something like this, but it's just going to say title. So you're going to set your title. This is going to be empty though. Data series, you want to set to horizontal line. X-axis, our variable, since it's going to be along this line, our variable is just going to be, right, x is basically just going to be distance along the line. So as you can see, it sort of corresponds to relative to the origin. So that's good, right? So now y-axis, we want to be pressure, right? And then you would just click apply, right? And then so we can sort of analyze this real quick just to sort of explain. And this sort of represents what we saw in our wind tunnel, right? At the start, we have our peak pressure as the contraction cone squeezes that air, the velocity begins to increase and our pressure drops, drops, drops. And now in here along the center line would be sort of our test section where our pressure is at its lowest and then it begins to rise again, right? But it's not going to be back to the initial because there's going to be a bit of wake. So there's going to be like a low pressure wake behind it, right? Well, sorry, that's incorrect. I'm thinking of the other. Sorry, I'm thinking of the other. I just simulate this with a circle in the middle. I'm thinking of the circle wake. I apologize. But no, it's not going to instantly go back to what it was before, and that's gonna certain things are gonna affect that, like the diffuser, how quickly it expands the air, how long the diffuser is. So that's fine. So now I would do the same exact thing, add a new chart, but I name this one the velocity chart, right? So now I have my velocity along the center line, and it's not necessarily opposite, but obviously our velocity is going to increase. And as we saw along this test portion in the contour and the previous plot, as the velocity increases, the pressure is going to decrease, right? So see, velocity comes back to about 15 meters per second. So this is correct. This is good. All right. So now, um, that's good. So now we want to do dynamic pressure, I believe it wanted next. Oh, total pressure, but I'll do, oh, excuse me. I'm going to do dynamic pressure first. So if I bring this back up, just to, well, I'll bring up the pressure just to make my point. If I go to y-axis, you'll notice there's going to be for you no dynamic pressure. We have to make it ourselves, right? So what you're going to want to do is go to expressions, right click, new, right? And then it's going to bring up something like this. And in here, you can write your equation to find the dynamic pressure, which I have here. 1/2 times the density times the velocity squared. So make sure you spell this exactly how the program writes it or spells it, or else it's not going to work. Once you have it correctly, it should become italicized. Right? Like if I were just to do, obviously it unitalicizes because it's not correctly spelled. Now it's fine because it's correct, right? So this is good. But now what you want to do is you want to come to variables, right? New, right? I named it din pressure because I don't want to name the same thing. And that expression is going to be based off of the dynamic. This is the expression that's going to define the variable. I'm going to use the dynamic pressure, which I created, right? So now, when I come back to outline and I go to dynamic pressure along center line, right? And I, of course, set the data series to the horizontal line again. X-axis is the same, but I go to the y-axis now. Dynamic pressure is available for me to choose. And this once again represents what we see in the contour. Now, total pressure, this is what I'm going to do next, is going to be the dynamic plus the static. Right? So I'm going to go to expressions. I would add a new one. This time I'd make my total pressure, right? Which is pressure, which is refers to the static pressure in this case, plus the dynamic pressure, right? So now, because I want to treat it as a variable, right? So now I'm going to go to variables. I would once again add it. I named it just top pressure, right? And the expression we're going to use is the total pressure expression, right? So now, when I go to total pressure along center line, And accordingly, data series, horizontal line, x-axis is the same. And I use top pressure, right? I get my line. Now, interestingly, if I were to determine the ranges automatically and apply that, and this is up to you what you want to display, it's going to look crazy. You're going to say, well, this isn't really right. When I looked at the contour, the total pressure, seemed pretty even or constant along that center line. It's just because of the range it's using. So if I go back to 40 to 80, right, and apply, as you can see, our line is much more smooth, almost perfectly flat, which is sort of, what we're more expecting. So that's good. And now the next step, I need to basically do the same thing, but I need to plot the vertical distribution of the velocity, the dynamic, and the total pressure. Not the normal pressure this time, but I think I did just because I was curious. So we're going to want to make our vertical line now, which because we want it to, start at the center point, right? The center point right here, right? Now, if you take 1.2192 and divide it, actually comes out to 0.6096, right? So 0.6096 is going to control 3D viewer, right? I'll visualize the vertical and ignore the horizontal. Say I set 0.2 to 1, for instance, right? Right? But we want these both to be centered. So both are going to be 0.6096, which is good, right? Apply. And now 0.1 is going to be the low point of this. 0.2 is going to be the high point. Obviously the origin 0, and since it's 0.6096 tall, we want to pick 0.6096 for the height. We're going to do 100, right? For the sample size. Right, that should be good. And now we're going to come back down. Let's put the horizontal line back in because why not? And we're going to look at velocity along this vertical line, which is what I named the second line. Right, so now, right, named it accordingly. Data series, I'm going to choose location as vertical line now. X-axis is actually going to be the y-axis, right? For this. And the y-axis is going to be make sure you select velocity u. So now when you apply that, right, as we can see, um, velocity is going to be basically 0 to begin with, or at the edges because of the no slip condition, right? And we're going to see this velocity increase along the middle where uh, where the air is being squeezed. And due to those little corners, as I showed earlier in the contours, you have a bit of a higher velocity here, but as you can see, we get that 15 value that we want, which is good. And now for dynamic pressure, we've already done the harder work with creating the equation. So once again, our data series, vertical line, x-axis is our y, and our y-axis is din pressure, right? And here we go. We see this pressure increase like we saw in the contour. And then if we go to total, same thing, data series, vertical, x, y, y-axis is top pressure, right? Here we go, right? This once again reflects what we see in the contour and what we saw in the lone graph earlier, whereas in that mid 60 range. So this is good. Trying to see, I don't think I had anything else that I needed to do. All right, so yeah, there we go. If we drew a vertical line, this would be our pressure and our velocity values in that center of that test section. So hopefully that was helpful to anybody trying to do something similar. And thank you for watching.